Okay, so let's go on to our second discounted cash flow method of project evaluation. This is called the internal rate of return method, and internal rate of return is universally stated as IRR. So when someone says IRR, they mean internal rate of return. Internal rate of return is a discount rate or an interest rate, and let's see how it works. It's defined to be the interest rate or discount rate that makes the NPV of a project or of an investment equal to 0. All right. What do you do when you see a definition? You memorize it, okay? When I was a young spudster as an undergrad, I remember taking biology, and it seemed pretty overwhelming to me, and my complete strategy in biology was just simply memorize all the definitions, don't do anything else, and I got a solid A in the class. So I've kept that rule, has worked very well for me. Whenever you see a definition, memorize it, period. No ifs, ands, or buts, okay? So internal rate of return, discount rate, or interest rate that makes the NPV of a project equal to 0. So what do we mean by that mathematically? IRR is the interest rate or discount rate that makes this equation true. NPV equals 0 equal what our usual NPV equation is, except now, instead of opportunity cost of capital, I've put IRR in there. So we're going to play around with that interest rate until we find the one that makes this equation true, that makes the sum of all the project cash flows for one player, time normalized, add up to 0. Okay, so this gives us another way to evaluate potential projects. As usual, with all DCF methods, you want to establish, first of all, the opportunity cost of capital for the project, which, as beginners in the real world, that's going to be given to you by your general manager that you're working for, or a consultant like me, of course, another gratuitous self-serving plug. And also you need to put together for that project all of its cash flows, project risk adjusted, stupid manager risk adjusted. All right, so once we've got that, then we want to solve the IRR equation for IRR using those cash flows, those project risk adjusted cash flows. And then this is really nice because it's nice and intuitive. We can just say if the internal rate of return is greater than our cost of capital return, we should go ahead. And if the internal rate of return is less than or equal to our opportunity cost of capital return, we shouldn't go ahead with this project. This is really great because it's very intuitive. A lot of people like this method. That said, there's a serious problem with this method, which makes it not appropriate to use for most developers. In fact, most sponsors of any real estate project, whether it's buying a cash flow producing property and managing it for a while, or improving it and then selling it, or developing something from scratch. The IRR works pretty well for bank lenders, but not so much for sponsors of real estate projects. And let's see why. Okay, so when we solve this formula, okay, what we're going to do, for those of you who remember your pre-calculus algebra, once we do a little algebraic simplification on this, solving this is always going to require finding the roots of a polynomial or a real equation. If the exponents here are an integer, we'll have to find the roots of what's called a real equation, okay? As you may remember from when you were tortured in pre-calculus algebra, sometimes you might not have a real number solution to this. There might only be complex number roots, okay? Also, you're going to have multiple roots, and you're not sure a priori beforehand which root is the correct root. The NPV never has this problem, the NPV method, so we call it a more robust method. Okay, so graphically, the mathematicians of the world have done some great things for us, which we can think about vis-a-vis the graphics on this particular page. If we have projects looking like this or like this, where what are the characteristics of this project, except for a cash flow at, say, t equals 0, or at the very end of the project, all of the cash flows are either positive or negative. Okay, so in these cases where we have, for example, one negative cash flow at t equals 0, all the rest of the cash flows are positive, or a bunch of negative cash flows until the last cash flow where that's positive, or there are two more cases, right? We could flip this over the x-axis and get something like this. Okay, so we'd have one positive cash flow at t equals 0, and all the rest are negative, and I'll let you figure out the fourth one from this second one down here. In those cases, the wonderful mathematicians of the world have proven that the roots to the equation that need to be solved, this is with integer exponents, are going to be real numbers, and the smallest real root is the IRR. So that's really great. So what do these sorts of things look like? They look like cash flow diagrams for lenders, basically. But this here looks more like a cash flow diagram for a developer or a sponsor, or what we call the equity participant in a project, where maybe they have to invest in phase 1, and then phase 1 comes online and they make some money, but now they've got to invest in phase 2, and then phase 2 comes online and they make more money. So they have positive and negative cash flows throughout the project, and mathematically we can't say anything about the math required, or the numerical methods required to solve these. So in a case like this, use NPV. Why? NPV always works. NPV is the word and the light and the way. Okay, so IRR works very well for bond projects and loan projects, and in the bond world, when folks are talking to you about yield to maturity, all they mean is IRR, kind of a funny IRR of the project by the bond, where they evaluate with non-risk adjusted cash flows. Anyway, yield to maturity, a certain type of IRR that folks in the bond world use. All right, so let's apply the IRR method to our distressed seller problem. Remember our mission: invest in very safe stuff that is short duration, something like treasuries. Based on that, we went out and found that a diversified portfolio of that type of investment, we would expect to return 5% annually. So that's going to be our opportunity cost of capital. And distressed seller then comes along and says, for $100, I'll give you a treasury bond, and the treasury will pay you in 1 year $110. Okay, so how are we going to apply this? We're just going to apply the internal rate of return formula. We want to say that find this number, solve for this. So that everything adds up to 0. So I'm just going to plug in like we did before. Here's our cash flow at t equals 0, and I'm not going to bother dividing that by 1 plus IRR to the 0, because 1 plus IRR to the 0 is 1. But our cash flow we'd get in a year, our 110, I do need to divide now to discount it by 1 plus IRR to the 1. Then through the magic of algebra, I can multiply both sides of this equation by 1 plus IRR and do a little more work, and I get, as you can see in gray, 110 is equal to, you should verify this, do the little bit of algebra required to do this. 110 is equal to 100 times 1 plus IRR, and that leads us to our IRR is equal to 110 over 100 minus 1, or 10%. Okay, our IRR is 10%. Our internal rate of return for this project, if we pursue it, is 10%. Our opportunity cost of capital is 5%. And what's our rule for internal rate of return? If the IRR is greater than our opportunity cost of capital, we should go for it. So let's go for it and buy the bond. So there you have it. Okay. Here's another example which I'm going to say that you should solve on your own. The solution here, it's not much harder. It's actually not harder at all than what we just did, but you should make sure that you can get the same answer that I got here, just to make sure you understand the method here.